Okay, quadratic patterns. Here's a typical quadratic pattern. Okay, pattern number is usually the x variable and goes up consistently all the way to a high number. The number of cans in this example is going to be y. And in pattern number 1, how many cans? In pattern number 2, how many cans? In pattern number 3, how many cans? Any guesses as to the number of cans in pattern number 4?
10.
Thank you. How did you figure that out? Why 10? Why 10? Because it gets bigger by 1 every time. Yesterday I talked about the first difference and the second difference. The second difference, if it's a quadratic, is always constant. The first difference here between 1 and 3 is 2, 3 and 6 is 3, 6 and 10 is 4. That's the first difference. The second difference is the difference between 2 and 3 is, and 3 and 4 is 1. That helps me make predictions. Okay, if the second difference is 1, the first difference must be 5, therefore pattern number 5 must be 15. Okay? As Jonathan said, the second difference goes up by 1 every time. Okay. The rule that I'm looking for can be written in this format. Some x's squared, some x's plus a number. That is the general quadratic equation. And as a side note, sometimes we write that in a factorized form. Not today. We're going to write it in the general form of some x's squared, some x's and a number. Sticking with my letters for a moment, and I'll come back to this problem in a minute. If x is still 1, 2, 3, 4, etc., my new y is going to fit this equation. Okay? Putting 1 into this equation, right? 1 squared is 1. So it's going to be a times 1 squared, which we know is 1. And b times 1, because I'm putting 1 into the equation, is... What's b times 1? b, thank you. And then c is tacked on the end. So that's going to be my first term in a letter format. My second term, if I put 2 in for x, what's 2 squared? So it's going to become 4a. And I'm going to put 2 into this x as well, so plus 2b, thanks Ash. And then plus c. Putting 3 into here, both places, 9a plus 3b plus c. Someone help me with number 4. 16a plus 4b plus c, and so on. Coming back to my first difference, as I did with my pattern over here, my first difference is always the second term minus the first term, or my third term minus the second term, or my fourth term minus the third term. That's how I find my first difference. So in this case, I'm going to take the second term and minus the first term. What's 4a minus a? What's 2b minus b? What's c minus c? Nothing. 9a minus 4a? 3b minus 2b. And last one, 16a minus 9a. 7. 4b minus 3b. C minus c. Nothing. Second difference. 5a minus 3a. B minus b. Nothing. Christy, 7a minus 5a. Thanks, Ash. And then b minus b, Christy. Thank you. Notice that my second difference is a constant. Am I happy about that? Yeah. I'm happy about that because I know that I wound up with a quadratic, and I should have wound up with a quadratic because I started with a quadratic formula. So my second difference is constant, as it was over here. Now I'm going to compare my algebraic formula with my actual pattern. Okay, I'm going to compare this constant with the constant that I got in my actual pattern. I'm going to compare this first term with, first difference with this first difference. And then I'm going to compare this term with the first term in my pattern. Now, I've finished the algebra. What you have to remember is 2a equals the second difference. Are you okay if I write down there? Can you see? 2a is equal to the second difference, which is 1. So you have to remember 2a is equal to the second difference. The second thing you have to remember is 3a plus b must equal to the first difference, 2. And the third thing you have to remember is a plus b plus c must equal to my first first number in the pattern. Now, just so you can see how this works, you could equally do the second difference, 5a plus b, could equal the second term in the second difference. Second term in the first difference, equal to 3. And you could equally do 4a plus 2b plus c should equal 3. I'm just paralleling the algebraic terms to my actual equation or actual pattern. Now I've got a set of equations that I can solve for each one, and if I work from left to right, I can find my a in the equation, I can find my b in the equation, and I can find my c in the equation. If I look at this one here first, 2a equals 1, what's a equal to? Look, 2 times the number must give 1. What's a? Half, or 0.5. So, from my general equation, I can start by writing y is equal to half x squared. That is the first part of the equation for this pattern. 1, 3, 6, 10, 15. Half x squared. The second part comes from solving this problem. 3a plus b plus 2. I know what a is. It's a half. So half can go into here. What's 3 times a half? 1.5. What's 1.5 plus the number gives 2? What's b? Half. 0.5. So I'm running out of places to write, but b is also equal to a half by solving this equation. So in my general formula, b is also equal to a half of x. I'm just following this ax squared plus bx, and now I'm going to figure out what c is. Don't forget, a plus b plus c must give 1. So half, a is half, b is a half. What does that make c? 0. Because a half plus a half is 1, plus something else has to give 1. So c must be 0. So up here, c must be 0. Now, to prove that this is the correct formula, I'll show you that it works. Put 1 into here, and into here, and we should wind up with the number 1. 1 squared times a half is half, plus half of 1, so half plus a half is 1. So it works for the first term in the pattern. Now I'm going to check it for the second term in the pattern. Put 2 in for x. 2 squared times a half plus half of 2. 3. Look, it works. Let's try it for the third term in the pattern. 3 into there. 3 squared. Half of 9. No. Half of 9. 4.5. And so remember 4.5. And what's half of 3? 1.5. What's 4.5 plus 1.5? Look, 6 is my next number. Shall we keep checking, or do you believe me?